In lesson 12 for cycle 3, we're going to keep working with exponential functions and logarithmic functions. In particular, though, we're going to see how we can use what we know about logarithms and power rules, power laws, to solve some more difficult exponential equations. So we're going to do it algebraically, and we're going to use a variety of techniques. So first, we're going to use a technique that involves changing bases. In other words, getting a common base. So if I were to rewrite these two powers, if you got one power equal to another power, if I can get them written so that they have the same base, that means that I could just set the exponents equal to each other as an equation and solve that. So I know that if I put an exponent 3 on 4, it equals 64. In other words, 4 to the 3 equals 64. So I would like to rewrite this 64 in terms of the base I've already got here, so they could both have the same base. So I won't change anything on the left side. On the right side, I'll just rewrite 64 as 4 to the exponent 3, because 4 to the 3 is 64, and I've still got this x here. I put the brackets just to show that I have to raise everything to that exponent x. But when I take the brackets off, it really doesn't look any different. So it's 4 to the 3x. So since I've got 4 to the x plus 5 is the same as 4 to the 3x, it stands to reason that the exponents must be equal. X plus 5 has to equal 3x if this equation is going to be true. So I can just forget about the bases. I'm starting a new equation, but it's the same relationship, and that's all I care about, is find out what value of x is going to make it true. And then from here, I can just go about my business of isolating x. So I could subtract, bring the 1x on the left over to the right, so subtract x in other words, and I've got 2x equals 5. I could divide each side by 2, and that would be my solution. So x equals 2.5 or 5 over 2. It doesn't matter, I can leave it as a fraction. That's fine. So that would be my x value that would make the original equation true. Here's another one where we got one power equals another single power. I can't rewrite 8 as a power of 4, at least not easily. But what I can do is rewrite them both as a common base. They could both be rewritten with a base of 2. So in other words, 4 could be written as 2 squared. Keep the 2x on the outside. 8 could be written as 2 cubed. Keep the x minus 3 on the outside. And I'm going to put that in brackets just to remind me that they have to go together. Taking away the brackets, pardon me, I get 2 to the 4x, because remember, when I have powers of powers, I just multiply these two together. So 2 times 2x gives me 4x. And when I take away these brackets, I'm going to multiply these together, but because inside the brackets is a binomial, I need to use the distributive law. So what I get is 3x minus 9. And again, now I've got these two sides of the equal sign, one power on each side. Bases are the same. Stands to reason that the exponents can be set equal to each other as well, and then we can solve it for x. If I subtract 3x from each side, then it turns out that x has to equal -9. So when you're doing these types of ones with the common bases, what you want to look for is if you've got a single power equal to another single power. That's when you can use it. And then the powers that you want to use as your common bases are just the lowest ones, the lowest prime numbers. So 2, 3, 5, 4 is possible, like I did in the first example, but 2, 3, 5, sometimes 7, 6, whatever. These low numbers, try to think about if you can rewrite these powers as these equations as powers of these basic numbers. Here's some practice questions, which you can certainly do on your own, and you should, but I got a bit more to do for the lesson before you get to that. Or you could pause the video here and try these questions before going on. That's also a good idea. So, sometimes the bases can't be made into the same number. And if that's the case, we have some other techniques that we can use. We can use logarithms to help us with that because, again, logarithms allow us to rewrite things. So one technique, let's just start by looking at the problem first of all. 4 to the 2x minus 1 equals 3 to the x plus 2. At first glance, it may look similar to the first two examples we did, but the difference with it, and it is different, is that I can't rewrite either of the bases so that they're same. There's no way I can rewrite 4 as a base of 3 or 3 as a base of 4 or both of them as a base of something else. They're just too different. The bases are just too different from each other. So here's what I can do is I can take the log of each side. So taking the logarithm of something is a mathematical operation, just like adding or subtracting or multiplying or dividing or you name it. As long as I do the same thing to both sides of an equation, I'm keeping it balanced. And taking the log of each side is no different. So I could take the log of 4 to the 2x minus 1 and the log of 3 to the x plus 2, and they're still equivalent. Now we can start to bring in some of the rules we know about logarithms. I can bring these two powers down in front of the logs as a multiplication. So I could now write it as 2x minus 1 in brackets times log 4 and x plus 2 times log 3. And then I want to use the distributive law. I want to expand things out. My goal is always to isolate x, right? But x is really buried right now. So I'm going to have to do quite a bit of work maybe to get x by itself. So I'm going to start by expanding things out, get them outside of the brackets. So I'm going to use distributive law on both sides of the equation. I'm going to multiply 2x times log 4, and I'm going to get 2x log 4. I'm going to multiply negative 1 times log 4 and just get negative log 4. On the right side, I'm going to do x times log 3, and I'm going to have 2 times log 3. So this is just the result of using the distributive law. Again, my goal is to isolate x, right? And it's often been our goal in math. So what I want to do is I want to get my x terms together, and I want to have constants together. So I'm just writing these things down because I'm going to highlight my x terms in green. 2x times log 4 is an x term. It's got an x in it, as is x times log 3. That's also an x term. Constants, negative log 4 is actually just a constant, right? It's just a number. I can type it in my calculator. If I go take the log of 4 and then make it negative, gives me negative 0.3979. It doesn't matter what it is. It's just as long as you understand that it's a constant. So log 4 is a constant, as is 2 log 3. It's going to be a number. It doesn't matter what that number is right now, as long as we recognize it's just a constant number. So let's bring all my x's to one side like we always do. And so I'll leave the 2x log 4 on the one side, but I'll bring the x log 3 over, changing the sign as we're used to doing. So these are all my x terms on the left now, and I'm going to keep bring my constant terms to the right. I'll keep the 2 log 3, but I'll bring the log 4 over. And we're on our way to isolating x. Now our next obstacle is I've got 2 x's going on here. If I want to isolate x, I can't have x in 2 different places. I can only do this isolation thing with 1 x. That's where common factoring is very handy. I can take x out of both of these terms. If I divide both these terms by x, then I'm left with 2 log 4 minus log 3. The x has just been common factored out into the front. And I haven't done anything to the right side in this step. Finally, if I want to get x by itself, what we've got over here on the left is x times this bracket, which is really just a constant. Again, 2 log 4 minus log 3 is just a constant. It's just that we haven't typed it into our calculator. But it's just multiply. So if I want to get it by itself, I can divide each side by 2 log 4 minus log 3. That's going to make it go away on the left side. And I'm going to have a division on the right side that I can type in my calculator. So this is what goes into the calculator. 2 times log 3 plus log 4 divided by 2 log 4 minus log 3. Now, I'm not a big fan of the calculator on my iPad. For some simple things, it's okay, but I'm going to actually use my other calculator, my real scientific calculator, because I'm more comfortable with that. But I'll show you what I'm doing. So let me just turn on the camera so I can show you as I type it in. So I had 2 times log 3 plus log 4. That's my numerator. I'm just going to hit equals at this point. So that all simplifies down to 1.556. Then I'm going to divide it by my denominator. I'm going to use brackets so I can do it all at once. So I'm going to put answer divided by bracket, and then 2 times log 4 minus log 3, end bracket, hit equals. And that should be my overall answer, 2.1407, etc. So x equals 2.14. If I round it a little bit, that would be my answer overall. So you might want to just pause the video and go back over those steps for a minute, because there's a lot going on there. It all makes perfect mathematical, logical sense. But if you got lost anywhere along the way, then obviously it's hard to follow the end result. It's a good one, though. Definitely a good example. Now, this last example is a little bit more esoteric, by which I mean a bit more of a special case, but let's take a look at it anyway, just so you can see another kind of twist on what can be done. If I want to solve this equation algebraically, I don't have one equation, so one power equals another power like I started out in this one. Remember, way back at the beginning of example 1 is just power equals power. This one's got 2 powers on the left, 2 to the x minus 2 to the negative x equals 4. So what this is going to end up being is a quadratic. There's no way to really recognize that other than after you've done a few. And again, it's kind of esoteric. In other words, kind of a special case, but here's how I'll show you how we can make it quadratic-ish. Let's rewrite this. I don't like that negative exponent there. I mean, it's fine, but I think a lot of people still struggle with that a bit. So let's rewrite it as a positive exponent. And let's even bring the 4 over to the left-hand side. Now, if I want to, I don't like having that fraction in the middle. So if I was to multiply everything by 2 to the x, so if I multiply each term, let's imagine going through and multiplying each term by 2 to the x. So I'd have 2 to the x times 2 to the x. I'd have 2 to the x times 1 over 2 to the x, and I'd have 2 to the x times 4. And I could even, if I wanted to, write 2 to the x times 0, but anything times 0 is just going to be 0. So I'm multiplying everything by 2 to the x. When I simplify this, remember, let's go back to another power rule. Multiplying powers are the same base. We add the exponents. So what I've just highlighted in yellow is going to actually become 2 to the 2x, 2 to the x plus x, which is just 2x. And when I multiply 2 to the x times 1 over 2 to the x, these just cancel out, so I'm just left with minus 1. And when I do this part here, there's nothing wrong with that, except it's kind of awkward. Normally, we'd put the 4 out front, so that's what I'll do. So there's minus 4 times 2 to the x, so just rearrange it. And finally, of course, 2 to the x times 0 just equals 0. All right, let's rearrange it a little bit more in decreasing powers. So let's go 2 to the 2x, and let's move the 4 to the 2x times 2 to the x to the middle, put the minus 1 there, and let that equal 0. Okay, it may not look like it's quadratic-y to you at the present time. Actually, there's one more thing that might help make it look more quadratic. Let me just erase that for a second and rewrite it as 2 to the x all to the exponent 2. So remember, this is equivalent as well. All the ones that I've written in yellow are equivalent to each other, because if I was to use the power law here, that would just become 2x again when I multiplied it out. So just playing around with the numbers a little bit. But you may or may not recognize this as kind of a quadratic. And it may look more like a quadratic if I do something like let, I don't know, 2 to the x equal m, or pick just some number. So I'm going to let m equal 2 to the x. If I do that and replace everywhere I see 2 to the x with m, I end up with m squared minus 4m minus 1 equals 0. And now it should be obvious to everybody that it looks like a quadratic. So the first thing I can do is try to solve this quadratic to find out what m is equal to. That won't be my final solution, but that'll get me along my way. The only problem is that, of course, there's nothing that nicely multiplies to give negative 1 and adds to give negative 4. So we're going to have to go with the quadratic formula in this case. But that's all right. We can handle that. So using the quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. That's what we get, or that's what we put in. Negative 4 is positive. And this should have been negative 4 squared, shouldn't it? Negative 4 squared is 16 plus 4 gives me square root of 20 over 2, so it's simplifying down nicely. Putting that in my calculator, I get, and I won't bother showing the work this time, but I get 4.236, and I also get negative 0.236. Okay, but that's not the final answer, because no one asked us to find out what m is equal to. They asked us to find out what x is equal to. Luckily, we have our let statement back up here to relate m to x. So now I can take these two solutions, and for example, for this first one, I can put 4.236 equals 2 to the x. And I just switched to green so that I could show as a different step. And then I can solve this. And if I solve this for x, then I'll have a solution. Again, we've got a problem where our variable is in the exponent, so hopefully you're starting to think, well, okay, if it's the exponent, I'll rewrite it as a logarithm, because logarithms isolate the exponent. So I can now write this as something equivalent as log base 2 of 4.236. And then I can use my change of base formula and just do the log of 4.236 log divided by the base, which was 2, and I got 2.0827 and so on. But let's round to 2 decimal places. So that's great. there's one of our solutions. But there could be another solution because we had that other value of m as well. Let's do this one in purple. So if we do the same steps, and then rewrite just like we did before. That's a 3. And then do our change of base formula again. So take the log of negative. Where's negative on this calculator? 0.236. Okay, take the log of that. Ooh, error. Why do we get an error? The reason we get an error is because we can never get the solution of we can never take the log of a negative number. Remember back to our log values, our log graphs, our log functions, that's the word I'm looking for. X never goes below 0. Let's go to Desmos just as a reminder, quick sketch. We're basically using y equals log base 2 for this graph, log base 2 of x. There's our function. Remember how we have a vertical asymptote on the y-axis. X cannot go below 0. It's not defined for values less than 0 of x. So when we try to calculate the x value, trying to take a log of a negative number, it doesn't make sense. And so that's where we get our error from. So there's no solution based on this. So anytime we get to a situation like this where we have a negative number, anything that requires us to take the log of a negative number, let's put it that way, is going to give us an error. So we can just consider that an extraneous root. So as I said, you finish writing this. I can't think of two things at once. Okay, as I said, this is kind of a funny special case, but it does illustrate some important points, especially the one about not being able to take the log of a negative number, but also this idea of maybe doing a substitution temporarily to help us simplify things and then coming back to it.